most of you have probably heard the last few years it's been 40 multiple choice questions. It's a Scantron thing. You're allowed to use the pages in the back of your lab notebook that you've handwritten. So any information that you're a little bit sketchy on, make really good notes of it. You can write on both sides of the pages. I would assume that the infrared spectra table inside the back flap is legitimate for you guys to use. But just in case, I'd make a note of the ranges of the more specific absorptions that show up regularly. So a carbonyl group shows up between like 1600 and 1750 or so. That's usually the strongest absorption. The hydroxyl group is a big fat one up at 33, 35, 3000. The carbon oxygens can sort of migrate all over. They're generally pretty sharp, and the CHs are sort of choppy, but the expected range is up a little bit lower than the hydroxyl group. So I'd write at least those four down, those four ranges down, to just in case he doesn't allow you to use the table with absorptions and functional groups in the back page. But again, I think he probably will. All right, so we'll go way back. The first experiment you guys did was the aspirin, isolating aspirin from the tablet. Excipients. People know what excipients are? Remember what excipients are? That's the junk filler that they add to the drug in order to make the tablet. Generally, it's chemically inert, so that's just stuff that you have to subtract away from the weight of the acetylsalicylic acid that you've isolated for your percent recovery calculation. Now, we did two types of filtration in that first week. You did, remember fluting the filter paper? You made the little fan type thing. The reason that you did the fluted filter paper is by folding it the way that we did, it increases the surface area that the solution comes in contact with for the filter paper. So when you're filtering something like the acetylsalicylic acid that was dissolved up in that solvent, that allows it to drip through the filter paper more quickly, because there's a distinct chance that if the solution cools, some of your product may solidify or crystallize while the solution is in the filter paper. So you want it to run through the filter paper into the flask more quickly. That's why you introduce the folds to the filter paper. Now, that filtration, we used the glass funnel that has a little stem on it. They call that a stemmed funnel. The other type of filtration that we did is the vacuum filtration. We used the Buchner funnel. That's the little, or not the Buchner funnel, the Hirsch funnel. That's the little porcelain one that has the tiny little pieces of filter paper. Now, generally, when you're doing a vacuum filtration, the vacuum filtration is used to isolate the solid. You remove the liquid that it crystallized in, that goes through into the sidearm flask. When you're doing a gravity filtration, such as with the fluted filter paper, that's to remove the solid impurities from the product that's dissolved in the liquid. So those are the two types of filtration that you should be aware of. And that we used them both in the aspirin experiment. Now, how many milligrams in a grain? There may well be one strange question on it about that. You've never actually used that again after this experiment. But make a note, it's 325 milligrams in 5 grains, which gives you 65 milligrams in a grain. I think I've seen a question on the final about that, but probably not for a year or two. So make a tiny little note on a corner of a page that that's the case, 65 milligrams for 1 grain. What else? So the calculation that he talked about there is percent recovery. No, it's percent isolation. he uses the same terms interchangeably, which confuses the hell out of you guys, I'm sure. But in this instance, it's percent isolation. So it's the amount of the acetylsalicylic acid divided by the weight of the tablet times 100. It's the exact same calculation as a percent recovery that we used later on with the cinnamon experiment, where it was the weight of the cinnamaldehyde divided by the weight of the cinnamon bark that you started with, times 100. So, and those are both different than the percent yield. So don't confuse the terminology. They're not interchangeable because percent yield is different. That's about all of the notes I have for that first experiment. Does anybody have any questions about the aspirin? This was just a very rudimentary experiment for you guys to sort of learn the glassware and know some of the terminology. Yeah? Gravity filtration is to remove solid impurities from the dissolved product. So the junk collects in the filter paper and the good stuff is dissolved up in the liquid that drips through the filter paper. Now vacuum filtration, that's done on the Hirsch funnel, and that is to isolate the solid product. The impurities in the solution or the solvent that are recrystallizing go through the filter paper and they collect in the vacuum flask.
So the Hirsch funnel, we receive the solid.
Yeah.
What about the
Well, the Hirsch funnel is always with the vacuum filtration. Gravity filtration, you will set presumably in this experiment, your acetylsalicylic acid is dissolved up in the hot ethanol. It runs through the fluted filter paper quickly through the stemmed funnel. It drips into the flask, presumably, or beaker, whatever it is you filtered into. And then the product is in the solution, and then it solidifies in there, crystallizes in there, or precipitates in there. So the product goes through the filter paper as dissolved species, whereas the gravity or the vacuum filtration, the product is the solid that stays on the filter paper. Okay, does that make sense? Okay. Anything else for that experiment? We're good? Okay. All right, so moving on. Oh, well, do you want to hold off on infrared spectroscopy till the very end, or you want to jump into it now? Because I know that's sort of a black hole for a lot of you. You guys, from the answers I've been getting consistently, it's still... Do you want to talk about it now, or should we save that till the end after we covered a bunch of them?
The end. The end.
We're good with the end? Okay. All right, so we'll go back and we'll review some of the spectra from the earlier experiments when we get that far. All right, so the second experiment that you did was the steam distillation. So that's the first of 3 experiments dealing with distillations. The steam distillation is when you add water to the solid, which has a volatile component to the solid, and by boiling the water, the steam carries the volatile solid with it up the condensing apparatus, the Hickman-Hinkle stillhead. That name was actually been on a final question, so make sure you write that down. So the steam carries the cinnamaldehyde in this case with it. It travels up the Hickman head, comes in contact with the cold stuff, and condenses, and it drips back down in. You go in with a pipette, you suck up the mixture of the two, and you remove it as it's distilling. Now it starts out being milky because the cinnamaldehyde is a fairly organic compound and it's not terribly soluble in the hot water that it's been condensed with. But as the distillation proceeds, the distillate becomes less and less cloudy because most of the cinnamaldehyde has been removed at the early part of the experiment. So the first milliliter or 2 that you collected was very milky. Towards the end, it was just sort of a cloudy looking solution. Okay, so that's the steam distillation in a nutshell. We sort of moved on from there to liquid-liquid extractions. In this instance, The cinnamaldehyde was just marginally soluble in the water, in the hot water. So when you added an organic solvent to it and shook it, the cinnamaldehyde pretty much quantitatively transferred to the organic solvent, whether it was dichloromethane or it was probably dichloromethane. So the dichloromethane is the bottom layer. You shake it the first time, it transfers most of it from the aqueous layer to the organic layer, simply because the cinnamaldehyde is a lot happier being dissolved in the organic layer than the aqueous layer. You did that 2 or 3 times to make sure that all of the cinnamaldehyde had been transferred to that bottom layer before you went ahead and pulled the top layer away and ran it through the column with the drying agent in it. And I think he gave it to the instructors to evaporate during the week. But cinnamaldehyde, or the dichloromethane, has a low boiling point, so that either went away quickly or went away and you weighed your product the next week. Yes, sir.
So is the purpose of steam distillation to isolate products based on their temperature, their boiling point?
Yeah, well, it's one of the ways that you can isolate something that's got a high boiling point from a mixture. In this case, it was the ground up or crunched up cinnamon bark.
Okay.
It's routinely used to isolate essential oils, which cinnamaldehyde is. But I think the introduction to the experiment sort of went through a little bit of that, essential oils. Let's see what other notes I got. So the big thing with this experiment is, hey guys, like dissolves like. That's going to be a theme that runs through the whole semester. That's something that you should have heard from your instructor. Like the cinnamaldehyde has a bunch of carbons to it. It doesn't have any very polar groups other than the aldehyde functional group. And the dichloromethane is a lot less polar, a lot more organic-y, or lipophilic, than the aqueous layer. So the cinnamaldehyde preferentially migrates from the aqueous layer to the organic layer. So that's what they mean by like dissolves like. Yes, the upper layer was the aqueous layer and the bottom layer was the dichloromethane. That's another point that I should make. Dichloromethane is more dense than water, so it's the only solvent that you've used all semester that is the bottom layer. Most of the other experiments, or a couple of the other experiments, used ether, which was the upper layer. So you have to pick and choose which upper layer and bottom layer you're talking about, because the organic isn't necessarily the upper layer consistently or the lower layer consistently. You need to know that ether is less soluble than water, dichloromethane is more soluble than water. Those two are organic layers that will not dissolve in the aqueous layer. What else? All right, so we can talk about the infrared spectrum at the end. Any questions with that one? So that's the first of 3 different types of distillation that you did. Steam distillation is sort of the least common, so why he chose to do that first, I'm not really sure, but that's that for you. All right, so experiment 3, that's the second type of distillation. That's simple distillation. Now, the only real difference between simple distillation and fractional distillation is that you can separate compounds with closer boiling points with fractional distillation, whereas you can't do that necessarily with simple distillation. The rule of thumb given in the lab manual is 40 degrees difference in order for simple distillation to work properly. And that was the case with the 2 compounds that we needed to separate. The hexane and the toluene had boiling points that were 42 degrees difference. The simple distillation, you just boil the liquid up, it condenses in the Hickman head, you remove it. The way that we analyzed it was with the refractive index. So you collected the first sample for the simple distillation, which we know was very much rich in the lower boiling component of the 2. And there was an intermediate sample that we collected. Some of you got it, some of you didn't. And then there was the final sample that you collected. And the final sample was mostly the higher boiling component of the mixture of the 2, so mostly toluene. And you brought your samples up to the refractive index machine, You added a few drops to the little well there. It took the readings automatically for you, and it spit out some numbers that you plugged into the equation that's given at the end of the experiment on page 62. So the numbers you need, absolute numbers, so you need a number that's 100% toluene, you will need a number that's 100% of the hexane. Those were provided to you. Those will have to be provided to you if he asks you to use that equation or asks you anything about the refractive index. Yes? Yeah, I think that's probably sophisticated for multiple choice questions. Just know that the background numbers that you were fed before you did your experiment with your numbers were 100% toluene and 100% hexane, and those numbers took into consideration the temperature in the room and the humidity and all that sort of stuff, so that the equation, when you plugged it in, when you plugged your experimental numbers in, actually worked properly. Gave you something reasonably close to that. Yeah?
Are you going to have to do the calculations for the multiple choice questions?
Bring your calculator. From what I remember, there were GC questions where you had to do some calculations, but we'll talk about that in the next experiment. This, I don't know. There may be questions on this. It depends on what type of mood Zach was in when he put the exam together. So, yeah, I would review, write down the equation on your free pages at the end of the lab manual, just so you have it in case. And it won't take up too much space to just write that general equation down. Excuse me. Yeah.
If you have extra notes for ourselves just as reference at the end, one of the things we're requesting is that each page has this experiment number all over it. So we can pull up the rest right?
Anything that's handwritten is fair game that you write in those back pages. You can write front and back. You can write size 5 font if you can write and read that small. And anything that you want to come in with is fair game as far as the open lab notebook is concerned.
But we would be tough for not having like experiment X.
Oh, for the lab notebook?
Yeah, if we had
Yeah, well, my students will lose points if they don't have the table of contents filled in and they don't have the pages numbered and the titles of the experiment written out. So, I don't know, the other instructors have their own criteria for grading the lab notebook. I think the lab notebook's only worth 50 points, so I would waste a lot of time trying to get every last point. Yeah?
About the table of contents, for the page numbers, you mean the pages that we wrote?
Yeah.
Okay.
So go through and number them if they're not numbered.
Okay, I didn't know if you meant like from the experiments.
Yeah.
Or if it's what we wrote.
Right. Well, that, for my students, it's that and having a reasonable number of observations. That's generally all I have time to look for when I'm grading them, because you hand them to me at the end of the period and I give them back to you like half an hour later. So I can't go through and read everything. But again, it's worth 50 points, so if you got it taken care of, otherwise spend your time studying for something more reasonable. Yeah.
So for the other experiment, we need like, let's say we wrote for like 4 pages, we need to write the other the same thing.
Yeah. Yeah, so number the pages, put numbers in the bottom corner, and it went from page 8 to 12, and the title of the experiment all in the same line there. No, just experiment 1 was from page 3 to page 7. Okay, so we're good with simple distillation? Yeah. No. Just the experiment that you've written, your pre-lab pages and the data pages. Okay, so fractional distillation. Fractional distillation, remember we used the long skinny screw thing, the Teflon had a pointy end and then it turned into like a screw that worked its way up through the column. All right, so that's the microscale version of fractional distillation. There's something called theoretical plates, which you may or may not need to know about. You probably won't. But the general way that the technique works is that screwy thing is spinning, and it's spinning so that the way that the spin thing is threaded is that it's pulling gas down from the top part of the distillation head. And by doing that, it's pulling down a mixture of the high boiling vapor and the low boiling vapor. But as it pulls it down, the vapor gets richer and richer in the higher boiling component. So the more volatile liquid manages to make its way up and condense and run down into the circular well there, where the higher boiling component gets pulled back down until you increase the heat sufficiently for it to work its way up the screwy, the vortex that the screwy thing creates in the air above it. So the lower boiling component will be what accumulates in the circular well of the Hickman head initially. And then you saw in this experiment, once all of the lower boiling component had boiled away, then you notice that your thermometer, the temperature dropped because there were no longer any hot vapors coming in contact with the tip of the thermometer. So you had to jack the heat up a little bit in order to make the higher boiling component work its way up through the screwy vortex that's trying to pull it down. And then once the heat was sufficient to make it work its way up that high, it condensed and ran down. And the latter half of the experiment was very much enriched in the higher boiling component. There was very little of the low boiling component present. Does that make sense? Yes, kind of? Okay, so the separation is much better because you have this mechanical device that's helping you separate the higher boiling component from the lower boiling component. Now, the way that we analyzed that was with gas chromatography. We haven't used chromatography yet. They sort of talk about it a little bit, but what's the two main aspects of any sort of chromatography that you should be familiar with? Remember, there's a moving phase and there's a stationary phase. In the thin layer chromatography, the stationary phase was the silica on the plate, and the moving phase was the solvent that worked its way up through it, dissolving some of the compounds more easily than others. With gas chromatography, it's you inject the liquid into a gas stream, and it partitions between a solid or a stationary high boiling liquid and a gas that's flowing through the column. Now, you know from the distillation that the first fraction that you collected is mostly lower boiling component. There's a little bit of the high boiling component that came along with it. And you know that the fraction 2 that you collected has a little bit of the low boiling component, but most of it is the higher boiling component. Now, for some strange reason, I didn't have previous year's lab manual to compare to this year's, but the connect between the distillation results and the chromatography was lost on at least half of my students until that's why you got the chance to redo those questions and resubmit them. Now, you know, fraction 1. Fraction 2. This is mostly low boiling.
Professor, can you either turn on the light or change the marker because I can't see A's?
I don't know where their lights are.
Is it that one?
Okay.
Just. Yeah, that makes it worse, right? Wait, that's good.
Voila.
This could be on YouTube.
So you inject fraction 1 into the gas chromatogram. the carrier gas carries it along. It volatilizes the lower boiling component quicker than it volatilizes the higher boiling component. We know from the distillation results that there's mostly low boiling component in that fraction with a little bit of the high. So the gas chromatogram that you see looks like this. You calculate the area under both of these, you turn them into triangles. You calculate the area, 1/2 the length times the width of both of them. You add them together, and then you divide that total by this, and then you divide it by this. And it will give you like 75% of this guy, 25% of this guy. And we know that the lower boiling component is the majority product. So that means the big area is the lower boiling one, and it comes out of the column first. So that makes perfect sense. You know that fraction 1 has a little bit of the high boiling component. The higher boiling component comes out of the chromatogram second, and this is a little nubby 25%. So the gas chromatogram makes perfect sense from what you would expect the results to be from the fractional distillation. Now fraction 2, you inject fraction 2 as a separate gas chromatogram. Fraction 2 we know is mostly the high boiling component, a little bit of the low boiling component. It's the same means of the separation occurring. You inject it here. Now we're going to see a little bit of the low boiling component and mostly the high boiling component. When you do the calculation, calculating the area under the triangles, add them together, turn them into a percent, and you will notice that it's 25% and 75%. Does that make sense? Now when you're doing this type of distillation, and there's only 2 components to it, you do 2 chromatograms. The first chromatogram shows 75 and 25%, so you should be able to know by subtracting from 1 that the second component is going to have 25% of this and 75% of this without even doing the math, right? Because if you've got 75% of the lower boiling component accounted for in the first chromatogram, there's 25% that needs to be accounted for yet. So you don't even need to see this to know that what's left over is going to be 25%. Right? Make sense? And same with the low, or the 25% high boiling. There's nowhere else for it to go. There were only 2 samples for you that you collected. So if it's 25% for the first sample, then it means it's 25 or 75% for the second sample. So it'll save you a little bit of time doing the areas under the triangles and whatnot in order to do the evaluation if that happens to be a question on the exam. Everybody's okay with that? You good? Okay. What other notes have I got? Covered that. You sure everybody's okay with this? Everybody said they were okay with it when I explained it in the lecture, and still, the write-ups were abominable. So, yes? Fraction 1, you get a little bit of the high boiling component coming over just because the separation isn't perfect. So the vast majority of it will be the lower boiling component because it's at that temperature range where the lower boiling component boils. And as you turn the heat up, then the higher boiling component will come over. And for fraction 2, where you did turn the heat up, there's a little bit of the low boiling component still left over, but it's mostly the high boiling component that you will recover in that half of the experiment. Yeah? You okay?
So fraction 1 is looking at 1 component.
Fraction 1 is what you collected first, what you sucked out of the circular reservoir with your pipette.
Yeah.
And that was the low from when you started boiling to when it stopped boiling and you turn the heat up. And that's when you turn the heat up is when this fraction came out. Mostly high boiling. Yeah.
I know it's multiple choice, but do we have any questions about like responsive error or?
No. None of the worksheets have asked for that, and I don't think any of the rubrics did either. So. Yes, sir.
So the calculating the area under the triangle, do you know do an example of that or something?
Well, if you have a ruler, you measure the height
Oh, in the base?
and the base.
And then
And
1/2
that's
base times
1/2
yeah.
times that is the area.
Okay. And then
Okay.
both, and then you just have the two components to get the percentages?
Yeah, add the two, and then divide by the area of this one, and
Okay.
divide by this one, and it'll give you the percentages.
Okay.
Normally, I think when he does that, he has it on a graph paper, so you can sort of tell how many blocks up it is and how many blocks wide it is, and then you can sort of do it. It ends up being unitless anyway, so it doesn't really matter.
Okay.
Okay, we're good with that? All three types of distillation? Everybody's going to be able to distinguish between them when there are questions? Okay, so moving on, experiment 5 is the thin layer chromatography. Thin layer chromatography, again, is we have a moving phase and we have a stationary phase. The moving phase is the silica powder that's adhered to that little plastic sheet or tinfoil sheet, whatever the hell it was. And the moving phase is the solvent that you prepared. You made, put it in the bottom of your jar and it worked its way up the plate. Remember the chambers, you have the sheet of filter paper in there, and that is called a liner. And the purpose for that is that the solvent also climbs up that. And once the paper is saturated with the solvent, it gives off vapors and it keeps the closed developing chamber saturated with solvent vapors so that the plate doesn't dry up before it works. The solvent works its way up to the top. So that's the purpose of the paper liner in the developing chamber. Now you had a slab of the thin layer plate. You had 5 solutions and 1 unknown. You needed to space them out equally on the plate. How did we check to make sure your spots were properly concentrated? Remember the UV lamp? You looked at them to see the spots. If your diameter is too big, when it works its way up the plate, it turns into a big blob. So you're not able to get an accurate measurement as to where the center of the spot is for the RF calculations. If you spotted it too close to the side, it sort of was influenced by that edge there not being clean, and that gave you weird results as well. Now, the way that thin layer chromatography works, you spot your samples on it. The silica that is the stationary phase is made up of silica atoms bonded to hydroxyl groups. Not one hydroxyl group, not 2 hydroxyl groups. There are 4 oxyl groups around the silica atoms. Some of them are hydroxyl groups, some of them are oxyl groups. But that makes that stationary phase, the silica that is adhered to the plate, extremely, extremely polar. It will be much more polar than any of the samples that you're applying to the plate. So remember what we talked about, like dissolves like. In this instance, like adheres to like, or like bonds like. When the samples that you spotted on the thin layer plate, the samples that you spotted to the thin layer plate ranged from being fairly non-polar to being very, very polar. The caffeine was the most polar. I don't remember which is the most non-polar. But you're getting these interactions between the stationary phase and the molecules that you applied in the sample. So caffeine being the most polar interacted most strongly with the silica stationary phase. The solvent that worked its way up around it had a difficult time dislodging those caffeine molecules from their interactions with the silica to allow it to travel up the plate. Whereas the non-polar components, whichever of those 5 drugs that we spotted was the most non-polar, that didn't interact terribly strongly with the silica stationary phase, and those interacted more favorably with the solvent, which flushed it further up the plate. So non-polar compounds travel up the plate the fastest. They have the largest RFs. Remember, RF is the distance the spot moves divided by the distance that the solvent moves. So RFs will always be less than 1. Whereas caffeine, which is the most polar, interacted most strongly with the silica. It stayed behind. It was binding to the silica preferentially to being dissolved in the solvent and working its way up the plate. So you can tell what the range of polarities of the molecules are that you're applying simply by what RFs they have. Molecules that have big RFs are nonpolar. Molecules that have small RFs are polar. That makes sense? Everybody's good with that? Yeah.
That last statement.
Molecules that are nonpolar interact most strongly with the solvent that's flushing up over them. So they get dissolved off of the silica and they travel up the plate. Whereas polar molecules interact most strongly with the silica stationary phase. They get held behind as the solvent is flushing past them. So polar means low RF, nonpolar means high RF. Now, how did we visualize these other than looking in the UV lamp? My students always skipped over that bit. The iodine chamber, yeah. And the iodine just interacts with some of the compounds that you wouldn't be able to see under the UV lamp. It stains them a brownish color. So 1 or 2 of you finished early enough to actually do that in my sections, but a lot of you, we just sort of skipped over that because it was sort of redundant. All right, let me see what sort of notes I made for this one. Polar, silica, that's good. On page 86 of your lab manual, there's actually a ranking of the most polar to the least polar. You might want to just write that down if you got a spare half an inch or so to cover that, just in case he asks something like that, or if there's a multiple choice question that might help you with that. And we talked about RF. RF is the distance that the spot travels over the distance that the solvent travels. All right, any questions with TLC? We're good with that? Okay, so moving on to experiment 7, the partition coefficient. Now you're getting into the more meaty experiments. And again, it comes down to like dissolves like. That's been a theme throughout all of these experiments, and that's the most important concept you guys should take away from Orgo 1 lab. The calculations with the KP is the, yeah.
So experiment 7.
Is that 6? No, experiment 6, I'm sorry. Again, that's the partition coefficient. So know that the partition coefficient is simply the amount of recoverable solid that's in the organic layer divided by what ends up in the aqueous layer. The aqueous layer is always the denominator in this case for this calculation. Now, the way that the experiment unfolded, you have benzoic acid. The first half of the experiment, you did a partitioning between an aqueous layer, pure aqueous layer, and dichloromethane. So benzoic acid is a somewhat organic-y molecule. It's got 7 carbons, and it's not charged. So it's going to be somewhat soluble in the organic layer, the dichloromethane bottom layer. But it's also capable of hydrogen bonding, so a little bit of it's going to dissolve in the aqueous layer. So we weighed out a certain amount of benzoic acid, you introduced the 2 solvents, you shook it, and the benzoic acid distributed between those 2 layers. Whichever one it was happiest in, that's where most of the benzoic acid ended up being. Again, like dissolves like. In this instance, with it being being a six-membered ring with a proton on the acetic acid. Most of it stayed in the organic layer. A little bit of it made its way into the aqueous upper layer, but most of it stayed in more of it stayed in the organic layer. Now the second half of the experiment, instead of straight up water, we used a weak base, sodium bicarbonate. So the sodium bicarbonate did an acid-base reaction that pulled the protons off of some of the benzoic acid, which makes it more water soluble. So you dissolved up your benzoic acid in the dichloromethane, you introduced the saturated sodium bicarbonate upper layer, you shook it, the bicarbonate pulled some of the protons off of the benzoic acid, some of the benzoic acid migrated to the aqueous layer. A lot more of it migrated to the aqueous layer for the second half of the experiment than for the first half of the experiment, where there wasn't base to pull the proton off and make it more water soluble. Everyone knows that salts are more water soluble than neutral species, right? So by introducing the base, you pulled the proton off of some of the benzoic acid, you turned them into a sodium salt. The sodium salt was happier in the aqueous upper layer than in the lower dichloromethane organic layer. Okay, and when you did your calculations, we evaporated the dichloromethane bottom layer in both halves of the experiment. So in order to determine how much of the benzoic acid was in the upper layer, you just subtracted what you recovered from the organic layer from what you started out with, the total weight for the beginning of the experiment. Does that make sense? And then in part two, a lot more of the benzoic acid made its way into the aqueous layer, which meant there was less of the benzoic acid in the organic layer. So when you evaporated the dichloromethane organic layer, there was less benzoic acid in that. But that meant that the numerator for your partition coefficient calculation was bigger. So that was significantly higher than the partition coefficient for the first half. There's sort of a number of loops that you have to jump through in order to get to that reasoning, but everybody's okay with that? Again, the neutral benzoic acid stays behind. That's happy being dissolved in the organic layer. When you introduce the weak base, the base pulls the protons off of the benzoic acid, turning it into a salt, so it migrates to the upper aqueous layer, which means there's less in the bottom layer when you evaporate it to dryness. So you recovered more benzoic acid for part one than you did for part two, but more of the benzoic acid was in the aqueous layer for part two than for part one. Okay? Everybody's good with that? A lot of twisty logic there. So that was a good, any questions for that one? We're good? All right, so experiment 7 is just an extension of that sort of chemistry. Again, it's separating things into two different layers. Either you came in with a 1-to-1 mixture of the solids, which my students did, or you may have come in with the 1-to-1 mixture dissolved up in your solvent, which some of the instructors did for you. But ultimately, you started out the experiment with equal quantities of the three compounds that are shown on the page there. Benzoic acid, benzocaine, which is an amine, and fluorinone, which is a ketone. So, again, we have like dissolves like. You dissolve that solid up, that solid mixture of the three compounds up in the dichloromethane, the bottom layer, and we introduced acids and bases to protonate or deprotonate the functional groups in order to get a reasonable logical separation. The first step that we did, we added 3 molar hydrochloric acid to it. The 3 molar hydrochloric acid protonates the amine group on the benzocaine. In doing so, it migrates from the dichloroorganic layer to the upper acid aqueous layer. it goes from being an amine to being an ammonium salt, which the salt is much more soluble in the aqueous layer. We shook it. We separated the top and bottom layers. The bottom layer still had the benzoic acid and the fluorinone because those have no functional groups that will interact with the acid. We did it 2 or 3 times to make sure all of the benzocaine had been removed. We combined those upper layers that have the ammonium salt in it. We added 6 molar sodium hydroxide to that. The 6 molar sodium hydroxide pulls the proton off of the ammonium salt, converting it back to the amine, the uncharged amine species. The uncharged amine species is no longer soluble in the aqueous layer, so it precipitates and you're able to isolate the solid. For part 2, now my students did this in a lot more rational approach to it than the rest of you may have or may not have. We steamed ahead and isolated the benzoic acid here. So we have the bottom layer that still has the benzoic acid and the ketone in it, the fluorinone. To that we added 3 molar sodium hydroxide. The acid-base reaction with the 3 molar sodium hydroxide is it pulled the proton off of the benzoic acid, turned it into the benzoate, which is a salt. The salt is soluble in the upper aqueous layer. We separated the upper aqueous layer. We added more of the salts to it, pulled more of the protons off the benzoic acid. Again, we separated out the upper aqueous layer that has the sodium benzoate in it. Okay? Ultimately, we put the proton back on the sodium salt by adding 6 molar HCl to it. The sodium benzoate is no longer soluble in the aqueous layer. When it picks up the proton, it becomes a neutral species, it precipitates out, and we isolated the solid from there. So that's 2 of the 3 components that were isolated with acid-base protonation chemistry. The bottom layer at that point only had the ketone on it. The ketone didn't interact with the acid or the base. It's immune to protonation under these circumstances. So we simply let the organic layer, the organic solvent, dichloromethane, evaporate between while the 2 solids were drying, and you came back and you weighed the culture tube that had the yellow residue in it. So the ketone was inert to both the acids and the bases. We separated out the benzocaine by protonating it, making it water soluble, separating the aqueous and the organic layers, turning it back into the neutral species, which precipitated it and allowed us to isolate the solid. The benzoic acid, we pulled the proton off, made it water soluble, it migrated to the upper aqueous layer. We put the proton back on with the 6 molar hydrochloric acid. It precipitated out of the aqueous layer again. We isolated the solid. The fluorinone just stayed there. It was a spectator throughout all the acid-base chemistry that was done in the previous steps. Okay? Is everybody good with that? Now the calculation for this was percent recovery. Why that's different than percent isolation, I'm not really sure, but those are 2 terms that Zach is happy introducing to confuse you guys. So in this instance, it was the weight that you recovered divided by presumably the 50 milligrams of the 3 components that were combined and given to you times 100. Yes?
So when you isolated that fluorinone, did you add any water to that?
There may have been excess acid or base in the few droplets of upper layer that had been left behind. So that was to sort of dilute that out to some extent. Anybody else? We're good? Okay. Moving on. All right, so experiment 8 now. The bromination of cholesterol. All right, so you added bromine to your dissolved solution of cholesterol. MBTE, methyl terbutyl ether. is the solvent that you used. I believe that's been a final question at various times during the year or over the years. So know what that is. It dissolves up the cholesterol. You're adding bromine and acetic acid dropwise until you see a persistent yellow color, the way that the procedure tells you. Why is it important to see a persistent yellow color?
It shows that it's
Bromine is the excess.
It makes sure that bromine is the excess reagent, which ensures that the cholesterol is the limiting reagent, which allows you to do a theoretical yield calculation. Okay? Everybody's cool with that? So you added the bromine to it. You isolated the solid. The yellow color went away. When you washed it with whatever solvent that we washed it with, you turned in an off-white or a white residue that dried during the week. You came back and you weighed it, and you took a melting point of it. That was extremely straightforward. You added bromine across the double bond. The difference in the infrared spectra was important here. We'll talk a little bit about it before we cover IR in depth. In the cholesterol, you have the double bond, which is a fairly weak but fairly visible absorption in the spectra. That peak goes away when you convert it to the cholesterol dibromide. You have a carbon bromine bond that wasn't in the cholesterol that shows up down around 600. That is from the carbon bromine absorption. So the comparison contrast between the two. One has the double bond, it's lacking the carbon bromine bond. One has the carbon bromine bond, the carbon-carbon double bond absorption has disappeared. So the infrared spectra in that instance was fairly conclusive as far as how well your experiment went. The chemistry is pretty much straightforward. I mean, why this one was worth 200 points, I'm not really sure, but the other earlier experiments were a lot more complicated. All right, so we'll talk more about the IR at the end. Any questions on cholesterol? Again, that was a really easy, straightforward experiment. All right, so the final experiment that we'll talk about is the Fisher esterification one, the banana oil.
Mm-hmm.
Now you measured out two liquid starting materials. You measured out your volume of acetic acid. You measured out your volume of the isopentyl alcohol. You combine those. The sulfuric acid, you added 4 or 5 drops. The sulfuric acid was a catalyst. Definition of a catalyst is it's neither destroyed during the course of the experiment. So the sulfuric acid that was there at the beginning is there at the end. It donated a proton temporarily, and then it took the proton back. How did we force the reaction to go in favor of the products?
Silica beads.
And there were 2 or 3 ways. I took silica beads as on the and my students' write-ups, but there were other ways as well.
Heat.
The calcium chloride that was in between the 2 little wads of cotton and the drying tube on the top that prevented any moisture from getting back into the reaction from the atmosphere. And
Heat.
what the other one was. I think it's just those 2. So my bad, it was only 2. So by absorbing the water and keeping the water out, you tie up one of the 2 products. And by tying up one of the 2 products, it not only prevents the reverse reaction because it was in equilibrium, but it also helps favor the product. The more water or more of one of the 2 products that's removed, it forces the equilibrium to continue towards the products. Does that make sense? So know that's probably somewhat important. The blue beads change color when they absorb water, and they effectively pull the equilibrium to the banana oil ester product. Calcium chloride, electrolysis. All right, so we did reflux for the first time. That was a new technique. A lot of my people didn't bother to tell me about that. Reflux, that's the reflux condenser. That's the water in the bottom and out the top tubey thing with the hollow jacket. The cooling water goes in the bottom, it goes out the top. The vapors climb up through that. They come in contact with the cold interior surface of the condenser, turns them back into liquid. They drip back into the round bottom flask underneath. That allows you to boil stuff for extended periods of time without the solvent evaporating and the reaction boiling to dryness. So that's a technique that you should be familiar with, or what that glassware actually accomplishes. Any questions with that? All right, so let's talk about theoretical yield, since this is the first one, or the second one, that actually comes into play. Now, one of my pet peeves with this whole Orgo 1 thing is when it comes to doing theoretical yield calculations. I get up there and I go through it step by step with each of my lab sections. I explain it. I ask people 2 or 3 times, do you got it? Everyone takes a picture of it. And they go home, and at least 40% of you have no idea what you're giving back to me in the write-ups. It pisses me